Nope,
Uh,
just a presentation. So
all
sit
right.
back, relax, enjoy, take notes. If you have questions,
Oh
they'll field
God,
questions afterwards.
for
Yeah.
visual space again. Nice. Let's do it.
Awesome. All right. Hello and welcome everyone to Celestial Theodolite update number 15. So we've been going over the spreadsheet the last 2 or 3 now. I think now I got some graphs here. So I'll go over a couple of the updates to the spreadsheet, break everything down, and then we'll go over the graphs and additions to the spreadsheet that have been made since I started working on it. So over here, of course, if you want to use the spreadsheet yourself or whatever, you'll have to make a copy of it. So you'll take this link here that I'm about to give, go make a copy. And then when you get your own copy, you can use the drop-down menu thing here. So anyway, we got drop-down menus for peaks, and then those corresponds to stars per peak. And then that'll fill in all the necessary information down here. And of course, we have our distance, relative mountain altitude, positions of stars at the time of occlusion, and then other various factors that we use for different computations, etc. So we got radius, standard refraction, an angle adjuster in case we want to do some testing and play around. M-bars, so we could figure out the pressure at our altitude if we want to figure out the accurate celestial refraction in stellarium. You can adjust your M-bar there, and this will update when your altitude changes, and then positions of the stars down here. So then we get into our predictions, which is just rise over run here for flat Earth. So we come up with an angle of 231 based off of the difference in elevation and the distance there. And then going over the globe, we do 360 times the distance over 2 pi r, which gives us an angular amount of 27 arc minutes. Even if you do 180 times the distance over 2 pi r, you get half of that. So you get 13.5 here. So if you subtract that 13.5 from the flat Earth angle, you get 2.17, which is the raw geometric globe. And then if you want to do the refraction stuff or whatever, all that is down here in a supplemental analysis, but we'll be primarily focusing on the raw geometric globe because that is what does the occluding. I don't think anyone disagrees at this point that there's an occlusion is a physical process. At some point, when you're no longer able to see an object, it thus has been occluded by said object and is no longer visible for you. At some point, that does occur. So the relationship there would be a true elevation or a relative elevation based off of drop over distance. So this drop over distance here that's computed as 27 as an angle, or I'm sorry, as 17 arc minutes as an angle, is also convertible from accounting for the drop over distance to the mountain. And then you convert that into another rise over run there, and that converts it into an angle. So you get 13 arc minutes as well. So these two methods achieve the same geometric location for where the position of the peak should be relative to that drop over distance there. So that is what the comparisons will be based on. So at the time of occlusion, since what does the occluding is the mountain peak and not the apparent mountain peak for the observer, we reference that position where the so-called true position of the star is, considering that as the light source, and that gives us an occlusion angle of 2 degrees and 33 arc minutes. So it was actually 2 degrees higher than our predicted value there. So we end up being off in altitude by 30 meters when we derive our angle off of the occlusion timing, or the occlusion angle, and the altitude of the peak. We get we get that. And then when we do the distance by doing the altitude of the peak and the occlusion angle, we get this distance here. So we can check our distances and elevation. So basically what we're doing is we're saying, hey, this angle corresponds to when this star wasn't visible anymore. And this also just happens to be what the raw flat Earth angle to the peak would be. Or in the other case, it would be, this is what the raw geometric globe angle would predict. So in other words, the relationship should be the star's true position gets gets occluded at an angle that puts it at what would correspond to 217 rather than 231. And then so from this, it's extremely important here to note that the way that we're deriving our distance and elevations isn't circular. So if we change the distance here, 1 second, let's just hard change the distance to 60,000. Oops. 1 second. I have one key that's broke on my keyboard. It's my 6 key. So that's what happened there. So anyway, you see the distance didn't change there because it's not derived. It's not circularly derived off of the distance. And that's extremely important here because when we look at other derivations where the refracted angle is attempted to use, a circular derivation is used where all 3 inputs are basically used, and then the output is a distance that agrees with what the globe predicts, but only after inserting the equivalent of the distance anyway, because they're just algebraically swapping it out. So we have this equation here that was given to us by the late great Ruhif recently, and we have here the distance it comes out with. I'm sorry, this is the starting distance, and then when it comes out to the derived distance here, well, how he derives it, we start with going over the drop over distance. So we start with the distance and the angle to get the drop. So it ties in the angle to that distance right off the rip, and then subtracting that from the peak elevation, which we'll do later for the actual comparison. If you want to use the refracted angle, you also have to use the relative elevation for that drop to make it that physical elevation. If that's what you would be claiming, that the physical elevation is 217, but it's lifted up at 219. So you'd be able to use the full physical elevation, but it also includes the full physical elevation here. So basically it's tying the angle to the true flat earth elevation and then locking in the distance to that. So what happens here when we change the distance parameter, oops, you're going to see his distance changes because they're locked in 1-to-1. It's circular. So this isn't like, no one's saying that you can't circularly put in the globe, right? That's not what we're saying. We're independently deriving it based off of the occlusion angles, not pre-cooking it in to derive the same thing that we started with, because all this is doing is just dividing over a different number, and that's not what we're doing here. These two are derived independently. Go ahead.
Basic trig is the comparison. That's what you do with the angle once you've already added your drop and refraction. That's the angle you use with basic trig to get the distance and elevation.
Yeah, you only use one of the, and you only use one of the other known variables. You don't use 3 of them and then like shuffle them around in a weird way where the ratio of them makes them all intertwined, because otherwise you would be able to adjust it and it shouldn't change it. And then also you could adjust the radius here when it's locked in like this, when it's circular. You can adjust the radius and make it anything and the distance still remains the same. So that's not good. So anyway, the purpose here, right, is how accurately can you derive your location based off of these principles of occlusion? Because we're told that the physical elevation relative to us, based on the geometry of the Earth, is that elevation is going to be lower, so it should correspond to a different timing, even accounting for the refraction. But they end up invoking refraction as basically 1-to-1. So what we're going to see here is in this analysis where we do 180 times the distance over 2 pi r to get the angular drop over distance, which we subtract from the flat earth angle, we're going to notice here that the amount of celestial refraction applied angularly is almost exactly the same amount of drop that they expect. And then of course we can convert that angular amount into a lift over distance the same way that we did drop over distance. And we can see how much they're lifting versus how much they predict in drop. So in the example of 200 meters in drop with celestial refraction of 14, they predict 186 meters in lift. So they damn near compensate for the whole thing. And in this instance, this is I think the only peak where they undercompensate by that, by 13 there. For every other instance, they either are equal to the amount or double or triple the amount of drop predicted. So that's an interesting thing to go over that we're going to look at some graphs over. So now that we all know what we're going to be looking at here, and for the comparisons, there's an additional mechanic to understand here. So when the true position of the star at the peak and the apparent position of the star at the observer location are very close to one another, it makes it so that the results are pretty much indistinguishable. So we've all heard the rhetoric of this method gives globe, it gives tiny globe, it gives concave, et cetera, all this random stuff. Well, if it doesn't give a measurement that's 60 meters better in elevation than the other model prediction, then it's ruled indistinguishable. And then for distance, if it's not within 1,609 meters, which is basically a mile, if it's not within a mile, in difference or better, then it's ruled indistinguishable there. So we have some thresholds there where we can try to falsify the null hypothesis, because remember, the null hypothesis is that the Earth is flat, so we have to falsify that. We can't falsify it with a measurement that's not better than what the other model predicts. We can only do it with ones that are better than the other model. So with that mindset in your head there, we can now go over some of the graphs here. So the way that the graphs work, when you download your own copy of this, there's a graphs table here, and you could pull data here and use these solo tabs here. So if you want elevations, you can come over here to the elevation tab, and oops, it's over here. These are elevations, and then distances are over here. And you can change the data range here. So we're doing Pikes Peak now, but say you wanted to do Blodgett or something, you would just highlight these, go down, press enter, and then it would show you Blodgett Peak. So that's how you would do the comparisons for those there. And then we have air bars representing 60 meters for the for elevations, and then distances again is 1,609 meters. And let's see here, we'll go back to Pikes Peak real quick. Okay, so we have two of these where you can look at side-by-side comparison, so you can see it really clean. And then we have a full group here excluding the North Peak data, because if you include that one, it skews all the other measurements and you can't tell any of the discrepancies here. But we have everything to do our own North Peak comparison here. We can throw those in at any time. But here's the side-by-side for all the elevations that scale consistently with one another. That makes sense there. And then, of course, we have the graphing of the celestial refraction versus drop over distance. So in Pikes Peak, they predict 200 in drop, but they got 186 in lift. Blodgett Peak, 101 in drop, 180 in lift. Cheyenne Mountain, 142 in drop, 320 or 230 in lift there, so on and so forth. This just goes on and on and on. And to kind of give a better image here, this is one of my favorites just because it looks like a silhouette of the mountain peaks. So if you had the mountain range here for each one of these, this is where the globe predicts it would be, or as drop, and then this is how much they're lifting up the mountain peak to compensate. All right, now I have to go to the bathroom real quick. So if Shane, if you could take over for a couple of minutes, that would be super.
Sure. You want to go back to your spreadsheet though?
Yes, here you go, sir. How's that?
Nice. So again,
All right, I'll be right back.
talking about comparing the angle you get from your prediction. So when you apply the plane trig, or however you get your prediction, you arrive at a different angle than we do. For Pikes Peak, if we're talking 231 versus 219 or 217, that's the angle that you use to get the second different triangle, which we're using to compare elevations and distances. We're using basic trig to compare either a known distance to, and then calculating the elevation, or vice versa. So that's the comparison that Alan was talking about with his graph there. That's what we're graphing out in the main chat. That's the comparison we keep talking about with elevation predictions. Because in reality, when you use the angle that we're talking about, it always equals the flat Earth measurement. That's why we keep bringing attention to it and graphing it and making little pictorial demonstrations and calling your attention to it, because that's the main principle that we're trying to argue. So when your objection is ignoring this completely and trying to talk about optic angles as observed from somewhere else, you're completely missing the point and not offering any sort of refutation to what we're putting forth. But we also have Alan's spreadsheet there on the back end on the right side. You see all these separate calculations and analyses that he's doing, which means in the case of each elevation and each calculated distance for the globe, how much of that was given via the geometric drop and how much of that was taken back via the celestial or terrestrial refraction. And what we're finding in all of these examples is that that ratio is almost exactly 2-for-1 or 1-for-1, meaning it's refracted just enough to bring it back up to the Earth drop, so that when we see in small observations when it becomes indistinguishable, that's only because the globe Earth prediction has enough sufficient drop and just enough celestial refraction to bring it back close to the flat Earth prediction from whence it started. And that's why it becomes indistinguishable. And that's why the graphs have an error bar where between 60 meters or whatever on elevation and about a mile on distance. So that's what we're talking about with the graphs here. Do we have any questions so far before Alan gets back? Any flat Earth questions? Anybody have anything to point out that we're not getting? Any objections?
Nope. I can
Nice.
think of.
I've got questions, but only Alan knows the answer. So
Well, I don't care what Jesse has to say, to be honest. Anybody else? We've heard Jesse's objection and lie through his teeth and not talk about anything and try to frame it in the worst possible light to his benefit without any, regard for the truth or what anyone's told him or what the actual goal is or anything. So I'm all set with that. Anybody else?
Oh.
Yeah. There's a question in chat from Daza that I was pinged about. It says, how do you reconcile your new flat Earth beliefs with other measurements of curvature, like the DEM that Google Earth uses to give most elevations, satellite-derived altitudes, and GPS locations in 3D space? And that question is for Dr. Mike. I'll forward it so that way it's at the bottom of the chat. Alright, so I'm going to put that in chat. So this is the question from Daza.
Well, I think he's trying to ask about, the ellipsoidal normal because we have ECEF and we have this reference ellipsoid from which the surface of Earth is based when they're doing heights and their H component or the Z component, right? They're talking about ellipsoidal heights above the surface of the ellipsoid. And when they even define ECEF within ellipsoid, they use that square within the circle diagram to show that they're both, quote, referenced relative to the surface of the center of mass of Earth. But in reality, they're just stacked over each other so that the orthometric height can be prescribed within the geoidal and the ellipsoidal. But that's not what this is talking about. Because of the H plus N coordination, it has to do with the geoid. It's how you get negative orthometric heights. Well, when you're trying to convert it orthometric to the ellipsoid, you got to use that equation, which is how you get negative orthometric height in the first place. To even have them is ridiculous. What mean sea level be? Talking about mean sea level now. Right. Yeah. Yeah, the relative to the center, but this isn't the time for this, Dad. This is a whole different discussion. We're talking about the celestial theodolite while in the bathroom. Did you have a refutation to the occultation times, any of the distances we're deriving, the elevations that we get from our predictive trig that doesn't comport with the globe? Does anyone have any objections to that directly? That'd be sweet to hear for one. Directly doesn't, the antithesis of the truth. Anybody else? The time that you observe the star isn't there. All right. When the time that you observe it isn't there is what you write down. So
All right, I'm back. Where are we at, lads?
All right, where you left off. We're good to go.
Nice. Is that guy asking a question about optics?
Yeah, no, it's retarded.
Okay, yeah, just gonna leave him turned down then. So Jake, real quick, bud, you know how we're discussing the celestial theodolite, and then right after that, you'll go, well, I don't understand why we changed the theodolite
exactly what he
angle.
did,
Yeah, we don't care about that all, right? We're not. We know that that's the angle for optically, right? We're doing occlusion angles and deriving distances and elevations off of those angles. So what you're talking about is not relevant at all. And I see Dazza trying to chime in over top of me, which is bizarre. It's like you have some form of autism where you think that when I'm speaking, you can just talk over me. That's not acceptable. So anyway, we are going to proceed now. Let's see here. So we went over air bars, graphing, how to use it, et cetera, differences. All right. So let's take a look at, let's see here. All right. Ooh. We'll hit up a little blend here.
Yeah, I was trying to call attention to this, the importance of the actual time and how you make the only observation is the time and how that time coincides with an angle. And then once we predict that angle is what we're using in our separate triangle to get elevation and distance. And that's what we're talking about with the graphs and what we're comparing mostly.
Yeah. Yeah. All right. So in the example earlier that I was talking about where we have a mismatch there, in the scenario where the true position, let's see, blend, first one. So in this scenario, true position at the peak is 221 and the observer star refracted position is 230 and the true position for observer is 209. And the, let's see, the predicted angle there for us was 1.34 arc minutes. The occlusion was at 20, was it about 13 arc minutes off. So anyway, here's a scenario where they end up being indistinguishable in terms of prediction, where it's a mix match, because it's like, which one is better here in elevation? And then the distance one is like, we're all kind of within the same threshold there. But anyway, so that's the air margin thing, how I was talking about it. So are there any questions?
Yeah, I have a question.
Greetings, sir. What is your question?
Yeah, I mean, the thing is that in our world we have about 0.5 to 1 degree of refraction, a refractive index in our atmosphere. So flat earthers, have to understand it. So my question to you is, where is that in your presentation? Because you can't exclude it, right? 14.7 psi is a pressure to the ground, so that atmosphere is always there. All right, so you need to include that. Tell us where it is and how that affects your arc second.
Well, the refraction between us and the mountain, which is what we're looking at when we're looking at the starlight, doesn't matter when we don't see the star anymore. All we care about is what angle that happened to be. Any refraction that's occurring on either side of the mountain doesn't matter, because the occlusion process is physical. At some point, a star was intersected by a physical object. So what angle was it when it wasn't visible? So refraction, explicitly celestial refraction, because that's super relevant to the celestial observations here, is accounted for. And we're looking at a comparison for drop over distance and lift over distance for celestial refraction. So in every case here, except for one, you'll see that they're double compensating or even triple compensating. So for like that old blend measurement that we were looking at, they predict 38 meters in drop over distance, but they have 131 meters in lift. So we're keeping a real close eye on it. But what we noticed when we look at the occlusion timings, so let's take, let's do Pikes Peak real quick, and then we'll look at the angular separation between true position and apparent position for the occlusion timing. So here, the angular difference is 14. Their predicted celestial refraction amount is 12. So it basically makes up the entire difference there to keep it there. And then when we look at something like, so keep in mind 14 arc minutes of angular separation between true and refracted, true to the mountain, refracted for the observer. And then we have, let's see, let's do where's Hound's Tooth is a good example here. So Hound's Tooth here, we have the closest distance possible, but look at the intersection timings with respect to true position and refracted position. 10 degrees 31 to 1036 there that are almost identical. The star gets occluded when it's intersected at the mountain at at 1037 there, and our prediction here is 1039. And so like you can see that the occlusion timing difference in angular separation between true and apparent is 27 arc minutes, or arc seconds. Sorry, arc seconds. So it happened like almost instantaneously when it intersected with the actual peak. So the occlusions are a physical process. So when you talk about if you bend the optical path and all this stuff, none of that matters. When you don't see the star anymore, there's nothing bending anymore for you. And that's all that matters. And when we use those angles and relationships, we can derive our position and relative mountain elevation more accurately than what the glob would predict, because the intersection angles do not correspond to the physical globe. Go ahead.
Okay, well here's your problem. When you were seeing the star before it's occluded, it's already past the peak. So did you account for that? It's already, for example, the sun is already set. We see 2 minutes later before it sets.
Yeah.
Before we actually see go down. So it's already below that horizon.
Yeah,
So
we specifically account for that.
Your star below? Did you account for the fact that your star is below Pikes Peak?
Yes, we specifically account for that by referencing the true position of the star and comparing the two. So at the mountain location, the peak and true position of the star have not yet intersected. For the observer, 50.7 kilometers away, they predict that the star is actually 2 degrees and 4 arc minutes below the peak already. But it's still observable for the guy until it intersects with the peak at 233. So it is already accounted for.
No. So you made a prediction. So let me try to say to you this. You are not going to know the true position of the star, because remember, your Earth is flat. Remember that, right? So when your star and when your star is past that mountain peak in a flat cosmology, right? You are telling us that the star is moving straight. It's not curving. It's moving straight. It cannot be occluded by that peak. So there is no angle in dropping or dipping or any angle change. Your star is moving straight ahead. So there can be no, hold on. There can be no refraction. There can be no refraction for lifting. Your star is moving straight. You do not have a curved path for your star.
All right. So let me correct a couple of things here. Number one, we're not saying anything about it moving straight or any optical contentions. That doesn't make any sense. And what was the other thing you said about the star moving?
Yeah,
What
yeah,
was your
it's
what was
moving
your
straight.
first thing?
Your Earth is flat. Your Earth is flat. Your sky is flat. Your star is moving straight. There's no drop. There is no drop. There's no angling down. Remember, visual angling down is just how you see things perspectively. So
Right. So
refraction is not on a
so check
flat plane.
so
Refraction
check
don't
so
exist. Go ahead.
so check this out, big dog. We don't say anything what you said about how optics work. What actually we say is that we see in curved visual space, and that creates the same effect of a dome of vision. So in terms of how the star moves and how we perceive it, those are all fine. And again, none of what you said refutes the fact that the star occludes when it intersects with the peak. That's the physical relationship. That's all that matters. What you're saying is completely unrelated to any of that.
Okay, no,
So
refraction, light,
yeah,
refraction, right?
right.
Light is redirected. That means the object has gone at an angle. So it is redirected it at an angle to the observer. If you're on a flat plane, your stars are moving straight. There's absolutely no reason.
Listen. Hold on 1 second, because this is where you start to conflate two different things. Where you're like flat plane moving straight doesn't matter, irrelevant. What's happening here is the occlusion process is happening with respect to the peak at an angle that it's not supposed to. Because if the Earth is a globe, geometrically, the actual elevation relative to the observer is going to be lower, thus a lower angle. So it can't be getting occluded at an angle that corresponds to no drop. So when you're saying like, oh, the sky moves star, you can't do it, all the stuff, you're conflating multiple things. And that's not like, and you're just saying refraction over and over again. Listen, buddy, if I can derive my distance and elevation based off of these, I'm doing it just fine. And all the variables are accounted for. When I account for refraction for the globe, it doesn't work. When I account for raw globe the same way I'm doing it, raw plane, it doesn't work. So like it's only working in some specific way when it's just the flat Earth angle. So when like your contentions are kind of moot at this point and you're getting real circular and just like restating refraction over and over again, and I can't really stand to listen to that any longer, unfortunately.
Because you didn't include refraction. Refraction is
No,
not.
it's specifically included. But
It's
okay,
it's specifically included and accounted for, and you still have a different timing prediction. So like check this out real quick before we move on, just to recap for the class here. Where's my Theo check Prezi? Theo.
Alan, you just have to factor in enough refraction for the globe to work, okay?
Yeah, it's so ridiculous. It's like, how much refraction do you want, big dog? There's already double and triple. Would you like more? How can I help you? Wait, where's my, dang it. Presentations.
Did you ever consider just maybe nuh-uh?
Yeah, for real. That's basically what it is. It's like, let me just loudly reassert refraction. You said you can find your distance using angles sub 1 degree below or above the horizon. I don't care about that at all. Shoot.
Nuh-uh.
Real quick. Hey, Bacon, are you available to talk in VC? I'm not sure if you participated last week because I wasn't here for it, but
I'm not sure my audio is any good because I'm using terrible earbuds.
No, it's not bad.
Sounds good to me.
You sound
Alright.
you sound good enough.
Okay, I'm cooking dinner though, but yeah, go ahead.
All right, real quick.
Well, no, I just wanted to. Oh,
yeah,
sorry. Go ahead, Alan.
You're good. Real quick, we're looking at a laser, a cup of water, and a knife. And you can see that once the laser, the light source, intersects with the actual knife, the refracted position disappears. So in the same relationship that we're looking at mountain peaks doing the same thing. And if in other words, the globe predicts that knife, it would be in a different position relative to where you see it. So it should correspond to a different angle when it should be at a different position when it gets occluded. and that would overlap with the, over the elevation of the mountain relative to the observer based on those drop principles. Now, when we look at refraction here, we have a point source of light. When we're looking at stars through a camera, they are, guess what, a point source of light. And what we find here is that the observer sees the point source of light, and this Dow occludes it when there's no refractive medium between them. It's just air, so the distance between this isn't very much, so there's not going to be a lot of refraction. So when you introduce so we're looking at the light source be occluded here. Now we're looking at the setup here, topographical. He lines up a stick to the Dow to the observer. So this is what's doing the occluding. This is the observer doing the observing. He saw the light source be occluded pretty much immediately when it intersected with the true position when there's not much of a medium between there. And then when we look at what happens when he adds a medium here, let's see if I can find the right one. Where's the one? Hang
By the way,
on.
Bacon, you should mute up again. I can hear you cooking.
Yeah, you're echoing a little bit. All right, so
Sorry,
he adds
sorry.
You're good. So he adds the medium here. This was the glass medium he introduced here when he put it over top of it. And then what that did is that changed the physical intersection angle between the light source and the peak. But once that intersection angle was crossed, the observer here could no longer see the light source. And I'm trying to find the exact frame that occurred. I guess we'll just play it out here. Just a couple of seconds. That's him lining it back up.
I have a specific
It's in the
question when you
middle.
get a chance.
Yep, 1 second.
Nope.
Oh, there it is.
Oops, my mic was muted the whole time. All right, so as you can see here, when he takes the medium out and puts the straight stick back to see the physical intersection angle, you can see that it's no longer directly touching the stick anymore. It's off a little bit. So refraction in this method is already accounted for. Even with refraction, there still has to be a physically different intersection angle. It can't be directly 1-to-1, because otherwise the light source would have to be like way down here to get through that medium. So that's not what's occurring here. So anyway, what's your specific question, Jesse?
Yeah, it's about it actually applies to both demonstrations, but the glass and the knife, are we on the same page in that if the water were removed from the glass and the glass were removed, but the knife and the laser were held in the same place, and that would change whether or not the knife was occluding the laser beam?
It would change the intersection angle relative to the source and the physical object, like the same that we saw in the example here with Goose's thing. So with no refractive medium, there's the intersection is pretty much 1-to-1, and then with a medium, it comes out to be it's off a little bit.
Okay, so the glass would be, and the water would be changing the angle at which the point of occlusion occurred.
Changes the intersection angle, yeah.
Okay.
Yep. So when people are like, "You're not accounting for refraction," we are. It's already there's still going to be a physical difference, right? We just saw it played out here, so that is the difference there. All right. So that was the refraction part. Was there anything else?
Actually, not really a question, but Jake mentioning, the sidereal time changing. Like, let's say we do go back to Pikes Peak. I think we should do the Pikes Peak observation again at the same time that the the first first
Same
measurement was taken.
same time next year or whatever.
Yeah.
Oh,
yeah, just kinda
100%
see.
agree. That would be super dope. I'm 100% on board with that, because that's how we would get like differences over time and stuff, and track other statistics and stuff based off of that. Super down for that.
Yeah,
Well,
I think that'd be cool.
I think he was also mentioning if you did it like every day in a row, and maybe you account for like the 4-minute sidereal day difference, and you try to catch it at the same time. Like if you did it like for 7 days in a row or 20 days in a row or something. And I think he was asking, would you get the same occlusion time if you account for the sidereal day difference? Would you get the same occlusion time day after day? And maybe he was trying to claim that refraction would change it so that it would be different on different days, rather than if it was the same, which would be interesting to actually
So
consider.
every day it's 4 arc minutes or 4 real-time minutes?
4
Real
minutes,
time,
like 20,
real
23
time
hours,
minutes.
56.
But they bind everything for cell nav, and the the graticule, all that is bound to 15 degrees per hour evenly, irrespective of any differences between the sun, the moon, and the stars, because like they all move at a slightly different rate, but they make them a uniform 15 degrees per hour for their references. So
Gotcha.
I don't know. So like I think trying to account for something outside of that's already accounted for by unifying them all. I don't know what that would add to the analysis.
Well, just that it takes 23 hours, 56 minutes for the stars to make one complete rotation. So in theory, if you were to do a celestial theodolite observation, the star occludes right at that time. In 23 hours and 56 minutes from that moment, the star should be in the exact same position of the sky. And so if you were to time it and do it day after day.
Oh, I kind of see what you're saying now. Okay.
And
So
I think maybe
it would be like
I might be.
it would be like tracking that gradual change every day. Oh, I don't know.
Well, basically, you're just trying to like, if you go 23 hours, 56 minutes every day, or instead of 24 hours, 23:56, and then you observe the star at that same occlusion point, it should technically occlude at the same time, like exactly 23 hours, 56 minutes later, 23 hours, 56, like day after day. I think maybe I'm expanding on his idea, but it's, first of all, would it do that, occlude at the same time? And then secondly, he might have been trying to claim if refraction was an issue, you might start to get different results, whereas if refraction is not, you would get the exact same timing. I don't know if he was taking it that far, but might be a way to like isolate refraction by doing it multiple days.
Isolate refraction. Huh.
Can't think of a
Well,
way
like,
that
if you
it's
got
not already isolated. Like, we're dealing with a one-sided measurement that is only dependent on a physical intersection. So like it's already hella super iced.
I guess it would just be that if you got different results, day in and day out, it could indicate to some people that maybe there is more of like a variable refraction thing happening. Whereas if it was the same and didn't have any, fluctuations, then that would indicate that maybe to some. I know it depends if you're only doing a few days, or some conditions are more consistent as well. But it would be expected that if it was refracting all over the place, that you would get different values. And if you got the same, it would show that more of towards the side that refraction is not a factor, because it's just the actual internal timing. And if you time that with the sky on a daily basis, it'd be interesting to see the results of that.
Do you think
Nice.
there would be a different angle?
It should be the same technically every day. Because it's like 23 hours 56, but there's like a couple seconds in there, so like if you try to get it exact, it should be the same.
Yeah.
Like every day.
Someone had a question for me before.
Oh, I just wanted to hear your
What?
thoughts on the Cell Theo in general. Just because I know you're a big fan of celestial navigation and that topic in itself.
Right. Yeah. Well, I haven't looked very much into this, just on its surface. Well, because it involves refraction and not just on the surface, then I'm not the right guy for that. Last week I tried to model a a reflection, a gradient for the globe. If that worked, then I could potentially give my take on that, but it didn't. So back to square one. If that makes any sense to you?
I couldn't really understand what you said, to be honest. You said you try to make a
Is it
model
the
and I lost
mic
you.
or? Okay, so here's the thing: if we're only dealing with geometry, not optics, then it's easy. I think I can figure all that out with geometry. But we're talking about an observation where refraction is also impactful, right? And there's not just refraction from the point of view of an observer at the surface. There's also the refraction of a mountain. And that's I never dealt with that, so I can't properly analyze that.
But do you know
Does that
the
make
point
sense?
of the point of the Cell-Theo method though is to use when you can't see the star, right? Because then you know
No.
that there's actual physical obstruction between you and the star, and then you just mark down the time, right? Regardless of all the refractive effects that happened before the star
regardless.
disappeared.
Yeah, it's not regardless because the star is going to be loomed up by the atmosphere, so the mountains, but they're going to be loomed up by different amounts.
No, right, Bacon though, but however much it is, no matter what, it's still at some angle. There's a point when the star is no longer visible, and the only thing we're concerned about is what angle did that happen to be. Because then all the variables that you want
the angle of the mountain.
Well, so if it's the angle of the mountain, here there's a problem here, because if we're on a glob, right, and we're an observer observing these stars moving over said glob, that angle that the mountain should be at, because glob drop, the physical elevation of that mountain should actually be lower, so it should be so that the time we no longer see it, its true position should correspond to a different physical elevation, and because otherwise that would be the elevation of the mountain with no drop, and if there's no drop, then the Earth's planar.
You lost me. Yeah, if you trace the path of light from an observer to a star, that's going to be a curved path. The occlusion of the star on the top of a mountain would be when the top of the mountain is intersecting that curved path. That's not the same direction. Like if you take a straight path instead of a curved path,
Yeah,
the occlusion would be sooner.
What kind of line would you draw for a star that's not there, though? It would just be a straight line to the peak, right?
No.
Yeah.
It'd be the same, but it would stop at the peak.
Right. So a straight line to the peak.
That's not a straight line. It's the same curve.
No, the star is not visible, so there's nothing curving to you to see. So it's just, where's the peak at? That would be it.
Yeah, so it's a curved line that hits the mountain, not me.
Well,
but still a curved line.
You're not seeing anything curved now. The light's gone.
Yeah, so the path of light from the star stops at the mountain. It doesn't reach me. That's why I don't see it.
Right. So it's not
It
curved.
doesn't-
So it's not curved. So it's not curved anymore. All that's left is just the line to the peak, my boy. You're getting it. You're getting it.
There is no light from the star to my eye when it gets occluded. I get it. That doesn't mean there's a straight path of light between the star and my eye.
Nope.
The
It means
path
that
of light
it means that
between
there's
the
no
star-
path.
There is a path of light between the star and the mountain. The light from the star is still hitting the mountain, but it doesn't reach my eyes.
Not when you can't see it. Well, what the hell does that matter?
Well, what do you mean? No, yeah, it doesn't matter. It doesn't mean the light is not hitting the mountain. It just stops at the mountain because it's hitting it.
Right. So ergo
Yeah,
occluded.
that doesn't make a straight. Yeah, that doesn't mean light is doing a straight path now.
I didn't say that. I
Light's
said
never
it's
doing a
not.
straight path.
It's not making any path anymore because it's been occluded. And all we're left
Yeah,
is a
to
straight
my
line
eye,
to the
there's no
mountain.
path.
Like,
That's
bro,
right.
we're saying
Wait,
the
wait,
same thing, bro.
Well, what does that straight line path to the mountain mean in reality?
Ooh, great question. So, if that angle were lower, then it would mean that the Earth is a globe, because that would mean relative to us, that mountain peak dropped geometrically by 200
Which angle?
meters.
Garbage.
It would be 218 because you would subtract 200 meters in elevation from it, which angularly comes out to 13.5 arc minutes. So you subtract that 11 arc minutes from 231 arc minutes, and you're left with 219 arc minutes. Well, 217, but then
You lost me at the beginning.
Anyway, so I'll walk you through it. Big dog. Are you tuned into the stream?
I'm cooking.
All right, no worries.
He's cooking at the moment.
No worries. Well, let me just
So you're talking
see if I
Ephraim's
can-
hypothesis.
Yes.
So it's a hypothesis. There's no evidence.
1 second. Is that Gary?
It is, yeah.
Yeah,
That is
you're automatically muted. There's no evidence. It's a hypothesis. Bro, you've invested 0 time in this conversation. We literally have a ton of videos backing up the measurements, the predictions, et cetera, et cetera. So like you can't just come in late and just say some nonsense and be drunk and all bewildered. You actually are permanently out of the conversation now, Gare Bear. Take care.
Okay, so I think we lost each other when I
Yeah.
mentioned that
That was beautiful.
there's
That
a
was
curved path. Okay, the path of if you remove the mountain for a second and see the path of light from the star to the observer until the star sets, it was taking a straight path the whole time. Sorry, a curved path the whole time.
Perceived
Now, if you
curved
put a
path,
mountain
sure.
in between,
Yep.
yeah, if you put a mountain in between, that curved path at some point would hit the mountain.
Indubitably.
Yeah. So when that curved path hits the mountain, that would be the same as the path of light right before, like at the instant that the star is right over the top of the mountain. The path from the star to the observer will line up with the path of light from the top of the mountain to the observer. Those are two light paths that are the same, but one starts at the star, the other starts at the mountain, and when they meet, they go together towards the eyes of the observer. So they land together in the eyes of the observer. So the observer would see both of those in the same direction. That's the direction in which the observer sees the top of the mountain. The star gets any lower, then the light starts hitting the mountain now. So you no longer see the star. So the last angle you see the star should be the apparent position of the top of the mountain. Right?
And it isn't until it intersects with the actual peak that it isn't visible anymore.
Right, let's say
Because
when
if
it's
it
right at the peak.
so if the Earth were a globe, right, the star has to get lower in the horizon because relative to you, that peak's, physically lower. So you're not gonna perceive its true position intersecting with the peak before that. So even though they predict that it's already down there at 2 degrees 4 arc minutes, it doesn't actually become not visible for you until it's actually intersected at 231. So it was never below the peak at 206. Like that's not where it was geometrically for the observer, because the occlusion timing shows that, and then based off of that timing, we can, where the star got occluded at its true position, we can derive our distance and elevation to the mountain more closely than what the globe can do based off of its geometric predictions to the mountain and their timing. Because, time equals angles for cell nav. So if we predict an angle of 230, that's going to be a different time than what the globe predicts at 218. So our angles can't be the same.
I'm lost already again. Yeah, I haven't been too much deep into this argument, so it's pretty hard to track.
No, you're good. You've been following it a lot better in this conversation than most people that have tried to refute it.
Last 15 times.
Yeah, so you're just talking about it honestly you're doing great, kid. But yeah, I highly
No,
recommend checking
honestly,
that
I think
out.
Bacon. Yeah, I think Bacon is actually one of the people I always wanted to talk to about this because of the cell navigation talks we've had before. So I think he would appreciate this method if he actually looked at it.
No, yeah, I understand the setup. Whether the numbers match the globe, or don't match the globe, or match with Earth, or don't match with Earth. I need to solve for refraction first. Then I can tell you about the number. Before
Nice.
knowing how to account for refraction the right way, I can't draw any conclusions.
No
Yeah, I
worries,
mean,
lad. It would be nice
in
to get
cellular-
some new analysis
Sorry.
in on it, though. No, you're good. Get some more people involved. So
Absolutely.
if you want to take a crack at it, get in there.
So Bacon, I just want to ask a clarifying question just to make sure. So first, your celestial refraction formula that you use, it has nothing to do with temperature and pressure, correct?
Correct.
Okay, just want to make sure that
If
that's consistent.
Right. Because if you don't plug in any temperature and pressure, it's usually assumed that the temperature is 10 degrees Celsius and the pressure is 1,010 millibars. That's what standard conditions are assumed to be. So that's the default. If you just go to a general refraction correction, that's going to be assumed. If you want to improve on that, then you can use your temperature and pressure. And I have that formula too. So if you do have that data, it improves the correction a little bit.
Okay. Yeah, definitely take a look. I want to see your analysis on it. Alan, do you have that spreadsheet available for the public?
Certainly do, good sir. It's in the chat now.
Bacon, I'm gonna message this to you so you can have it. I know you're cooking.
Bacon rocks and rules.
This is not Oblivion, is it? Who's talking to me? Except for Alan.
That was
No, I said you rock
Galatrax.
and roll. Yeah, I just said you rock and roll. I've been trying to get you to join in on the discussion for the past like 3 weeks because I know that you're an OS guy and you contribute very positively. I love you, Bacon.
Okay. Sorry, I missed that.
It was me, Beasticles, that inquired about your thoughts, and then that was Gally.
Okay. Yeah, I thought you were Oblivion for a second. It kind of sound like him.
I don't even know who that is.
Yeah, I mean, recently he has been absent.
Is there any other questions about the Cell Theo, its process, method, etc.?
I have, and I did submit them via a PDF, but I don't know if now's when you want to go over that, if you do. But I am here.
Might as well. What do you think, Alan? You have
Pulling
the
it-
PDF?
Pulling it up now.
Perfect.
Okay, let's see. The way I want to see if it's clean, or surface.
Put it on the screen.
Oh, yeah, right. Go ahead. 1 second. Download.
Jesse, as per the presenter's request, I just have to ask you that if you ask a question and someone answers you, you be ready to steelman or at least try to give what they answered you back. So if they answer your question, we might ask you to answer what they said to you back. All right?
Oh, that's clever.
Oh, that you'd have to actively listen to the answers for your questions? It's not clever.
Well,
It's just being good
All right.
faith. Yeah.
All right. We're going to get to the things now real quick. So, does it even work to measure the known delta height of mountains? Well, let's take a Gandy here. These are the questions, right? All 4 of these?
Yes.
Okay. So let's take a Gandy here. We got elevations. We got elevation. So Pikes Peak. Let's see. We got, yep, elevation. We're good. Blodgett. We're all within the same parameter there. So we're good. No one's better than the other there. We got Cheyenne Mountain I think no one's better than the other there. We have Blue Mountain. We take the cake on that one. We got Mount Rosa. We take the cake on that one. Got Green Mountain. We're good on that one. Getaway Mountain. We're good on that one. Actually, wait. No, I think we're close on that one. I think that one is a mismatch. And then we have Houndstooth here. This is one where they're all the same because the distance wasn't very much. And then we have Old Blinn here. We're all within 60 meters of each other. We have another Blinsky. We're out of the air margin there, but within 60 of the predicted of the glob there. And we have another here where the globe just barely slides in, I think, on that one. And then we are intersected there with them. So they're not much better than us in terms of our 60-meter accuracy there. And then we have Goose's measurement here, where we're all within the same range for who's more better and distinguishable there. And then when we do distances, because I assume that's going to be the next question, it's not on there, but I'm going to throw it in there for you for funsies. So is it accurate for finding your distances? Let's take a gandy.
Well, I'm not interested in the distance.
I don't care what you're interested in, though.
I think
So-
your math for the distances is wrong.
1 second, bud. We can go over what the math is for the distances here in a minute. And I'm going to go over the distances now. So for distances, we have Pikes Peak. We have 48. Yeah, we're much closer there. So 1,600 meter tolerance there. Blodgett, I think you're out of bounds. We're in bounds, but that was a mismatch on the mismatch on the elevations there. We have Cheyenne there. We are over on that one. You guys are just over as well, or you're not within the 1,600 on it either. And then Blue, we are closer to Blue. Mount Rosa, we're closer. Distances. Okay, now let's see. We got Getaway. We're both off on that one. We got Houndstooth, all the same. Old Blinn, about the same. I think we overshoot it by just a little bit there. And then hang on 1 second. You're hot, Mike, and fresh. All right. And then we got another Blinsky here where you are closer on the disty, but that was the one that was adjusted by like 30 meters because of the hillside slope or whatever. So it kind of makes it looks a little different there, but you guys get that one there. And then we have the other Blinn. We are just off on that one for distance, but again, our LEs were mismatched. And then we have distances for this all good here. Now, when you say that you disagree with how we're doing the distance, I am doing the mountain elevation, the one known thing, and then the occlusion angle, which is our dependent variable, which depends on when the star gets occluded.
That distance I'm okay with. If using that method, if Earth were flat, that would be the way to get the distance. But I don't agree with how you're doing that for the globe.
Okay. I have several globe methods here. Let's take a gandy and see if we can find one that finds your fancy. So we have celestial refracted globe using the 218 angle, which is the celestial refraction position at the observer location, which gives us 55,100 there. So they're off by 5,000 there on that. And then we could do terrestrial refracted globe, which in this case ends up being 219. So if we do 219, you're at 54,000. And then if we do spherical trig, we get 50,000 again, and another 50,000 doing different methods here. So one of these is like a arc chord, and an arc on the meridian. The other one's the chord length, and the other one is something that has to solve for gamma and then get a linear distance and do a thing and compare the two or whatever. Anyway, goes through different spherical trig functions to get distances there. More comparisons there using true position versus refracted position for the spherical trig to see how that affected it.
Dude, you want it hard on the spreadsheet. Oh my god.
This is the great circle arc stuff. So none of these match. This is using true position, though I don't have one for oh wait, yeah, I do. It's right here. So yeah, none of these None of these help. And then we have Ruhif's method here, which I went over at the beginning, does give the correct distance, but it's circular in derivation such that the distance is cooked into it to where if you change the distance here, like if I hard change this, it's going to hard change the distance to what it is. It's not deriving it independently, which is the purpose of it. So like if I change my hard distance here for the flat earth, it doesn't change my distance prediction because it's not based off of that.
Real quick, just a quick question before Jesse gets to his other ones. Bull Knight wants to know, how was the 60 meter tolerance chosen in terms of height, in terms of like the error margin, and the same for distance, which is 1600 meters? It's a good question.
Gotcha. The sky moves at 30 meters a second. So I put 30 meters on there. And because the elevation differences aren't very much, I just doubled it to 60 because it's, I mean, they're very, very close. So on that, I put in, and then for the distances, 1600 meters is a mile. So and then like the Royal Society standards for introducing a chronometer or whatever, like to solve their riddle or whatever that they put out in their ad in the 1700s, was to have half a degree of accuracy in the sky or in the sea or whatever to find their longitude, which translates to about like I forget how many miles, but to be like within a mile, that's basically what I said. If it's outside of that, then if either prediction is within a mile of one another, then they're basically the same, right? That was my logic behind it.
Sweet, thanks.
All right. Back to Jesse's PDF.
Oh, right.
Oh, we just answered that. Right.
So what is the stated margin of uncertainty for the method?
60 meters for elevation and 1600 meters for distance.
Okay, so am I understanding correctly that it is not reliable? There are cases that where it does not match the flat Earth prediction within the stated margin of accuracy?
Yeah, the same that there are for globes, but there's times when they're close together and neither are better than the other. Like for instance, the globe's never explicitly better in distance and elevation than flat Earth ever. It comes down to it might be better in one or the other, but that classifies as a mismatch. So it's our limit of use for the instrument, because if it gives an indistinguishable result, then it can't tell us, it can't falsify our null hypothesis there. So,
well, I'm not really interested in comparing whether it's closer to globe, because first of all, you're using the wrong math to represent the globe, and I'm glad to go over that with you. But
what's
like,
the right? What's the
or is this just a
I'm gonna jump in periodically and just interrupt you because I really don't care about what you say or how you say it. It's super annoying to go through this. We just went through all the globe predictions. None of them match. None of them do anything. None of them help. We went over Ruhif's. It's circular. There's no way to do it unless it's circular. I just showed it. You said it's wrong. You want to go over it? Okay, man. We can go over it, but
you're lying to people. You won't let the truth be told. You won't let the opposition speak, and then you just mute them or kick them or whatever.
Well,
first of all,
you don't have.
Okay, first of all,
what exactly
Jesse,
is your contention, Jesse?
1 second. First of all,
what's his contention exactly? That's like, what is it, bro? Because he went through everything.
Yeah, and first, we're not turning this into you said this thing over here, you're doing this or that. Because if you want to play the instances of people lying thing, bro, you never represent our position outside of when we're arguing it right here to anyone accurately. You lie to people directly to their face. So we're not turning this into that. So we're trying to stick to the actual measurements here. If you have a point of contention, you say that we're doing the globe wrong, go ahead and show that.
Specifically,
we're trying to go through your PDF. If you're not interested in our metrics in any of this, then why are you here? So does this make sense given what we know about geometry and physics? What kind of question is this, Gally? What would you call this? Like following this, what is this?
think
Wait,
he's just trolling. I think
This
he's
is
poisoning
just
the well. So
does this
it's like this
does it
whole-
make sense given the physics of what we know about geometry? I don't know. Does it make sense that the star has no idea where the physical elevation of the peak is, and yet it gets occluded at that angle? Does that like
Yeah, I
what?
don't like the whole like poisoning the well, which is like I'm gonna annoy you and say a bunch of stuff that makes no sense. And if you mute me, I already said you're gonna mute me if I do that stuff, so therefore I'm right.
Yeah. And to be clear, I
Wait,
have
wait,
no
to go back.
problem. And to be clear, real quick, I have no problem muting people or censoring them over retarded shit like this. I don't care. Anyway,
So
continue.
to go back on what he originally asked, like about
Mhm.
the globe having some instances where it was closer or it was
Mhm.
null, like it could go either way. How many would you say lean more towards globe versus flat? And then,
Well,
like, I guess how many were right in the middle? Have you like tracked
well,
exactly like a number?
yeah. So I should get the number out, but it's we can look at it real quick. It was the mismatches are, let's see, Blodgett and Houndstooth. Well, we already knew that. Getaway was one. So our elevations are similar. And then the ones where the elevations are low. So in instances where the true position of the star and the refracted position are about the same, that's where you get these instances where they're indistinguishable from one another. Now, they do get a better distance on one, but the elevations were all within the same threshold parameter. So it's not that they're necessarily better in distance and elevation. It'll be only one aspect of it. But that's just because of the, it's just how it turned out. But it's not
On the
like
ones,
it's, but sorry, go ahead.
well, on the ones for flat, is it all of them line up, or is it the same instance with the flat where only a couple line up and
No,
like some of them are off?
No, for flat, we blow them out of the water. Like they're not even close. Like it's conclusively one-sided on it. So like it
Okay,
goes,
but
go ahead.
no, but the ones for the globe that where they were closer, it was only what, like one or two of the whatever of the categories that were closer, or did it vary, or I guess
Yes. So within the two categories of elevation and distance, there's instances where they're closer in elevation, but not in distance, and vice versa.
Was there a third one? I thought there was a third one too. Like because I remember you saying something that they were off on a couple, but then they were on like some third. Maybe I misheard. I don't know. But I guess I just was trying to figure out exactly the numbers because I thought that there were none. Like from all of the stuff that I've listened to from you guys, it's like you guys kept saying that there's none that the globe matched up
Yeah.
with, and then I'm hearing that there actually are some that the globe
Yes.
matches or that are evened out. So that confuses me, you know.
No, it's a great point. So if you go by no air margin and just who's closest and like no like parameter set, then we're closer every time except for in the instance of Blend Mountain, where the true positions are basically the same as the refracted position.
Maybe you should tell her why that is though.
Yeah, well, like I was saying earlier, when we look at the old blend.
So that's
we
three so far, right? Or how many do you know, Jesse? How many total went more towards? Because I'm just trying to get numbers here. Like,
Well,
okay,
when you
that
say more towards, it would be like if they're both better than the other prediction, that would count as like a decisive one. So none of those exist for the globe where it's decisive. We have
were all of them.
we
Okay.
we have mismatch measurements where it's off.
You're
Or
saying within the margin of error, right?
right.
So like if neither are within the margin of error, then it's kind of essentially, I guess, you throw the measurement out and you have flat earth measurements that are within the margin of error that would conclude, this might be, or this would be an accurate measurement, where you're not seeing that with the globe is kind of what it looks like.
Yep.
Yeah,
That's
they're always off, and then sometimes they even overcompensate for what they actually predict. Sure, bro. Yeah, sure. Sure I did.
Could we
Sure I did.
go over the the math that you're using to calculate distance for a globe?
I was gonna say Jesse said that earlier, so he
Sure.
basically was claiming that so
Sure. So for flat Earth, I have the mountain elevation times the tangent of the occlusion angle. For globular Earth, I do mountain elevation times the tangent of their physical elevation. Oh, this one's for blend mountain. Let's do pikes so it looks familiar to me real quick. Okay. Yeah, so their physical elevation. So that gets their distance based off of that. And then for refracted, do the same thing, mountain elevation times the tangent of the refracted position, which is 218. For the terrestrial refracted globe, we do we do this one here for distance, which is main distance times the tangent of the terrestrial refracted angle, which is 219 there. For the spherical trig, we do, let's see, this one is doing couldn't tell you, doing a bunch of sine, cosine stuff and radius stuff. So we got that one there, and we got this one, which solves for gamma, which gives them like the angle from the radius of the Earth to the peak and observer or whatever. And then anyway, so we got all different distances here. Like which one would you like?
The very simplest one, the one because the celestial theodolite is claimed to measure the geometric elevation angle to the mountain. Let's just work with geometrics. Forget
All right.
refraction. So just pick that simplest one.
All right.
And let's look at the actual formula you're using to calculate distance for that.
All right. Mountain elevation times whatever the geometric peak of the mountain would be.
So the actual elevation difference from map, published heights, divided by the tangent of the elevation angle, right? Of the star at occlusion, right?
Mm-hmm.
Okay, I'm saying that is the wrong math to calculate distance on a globe.
Okay. Well,
So
Ruhif, hold on one second. One second. Ruhif entered his hat into the equation. So do you have a different equation than Ruhif's?
I don't know what Ruhif's is.
Okay. Well, I'll send you a screenshot real quick of Ruhif's.
You got Ruhip's globe and Jesse's globe now, I guess.
So
Well,
this
it's always
is
been that way because they both disagree, right?
well, it's all good. So hold on one second here. So let's get. It's got to scroll up a second. I think I overshot it.
And I did send you the formula that I claim is correct.
Ah, here we go.
In an example in a copy of your spreadsheet a week ago or something.
Oh, 1 second. I'll check that one. So here you go. So that's what Ruhif's using, but that ends out to be circular. The one that you sent me that gives terrestrial refraction, is that what you're talking about?
Well, I would prefer to use this one that has no refraction involved.
Oh, I'm not familiar with one that you sent me then. I only have the terrestrial refraction stuff that you sent me the other day. Send me the link to what you're talking about.
Well,
I'll pull it up.
Do you still have my PDF up?
Yep.
See if I included a diagram in there of a Earth curve drop scenario. Keep going. Is that it? Okay, let me tag you in the text chat. I've DM'd it to you before also. Hold on.
Is astral refraction just celestial refraction with a different name?
Yeah.
Okay.
Okay, I tagged you with a diagram. If you could bring that up, I'd be grateful.
if you're gonna say that they're doing it incorrectly, you should have the instant correction, right? Or your refutal or rebuttal.
Well,
I mean, isn't that why you brought it up to
I've
say
sent him the correction to old spreadsheets, but he did not run his spreadsheet by me before today, so I had no way of knowing what he was going to present today. So
and I almost never will.
Right, but you've had an hour and a half of him presenting. If you took issue with what he was doing and you say you're doing it wrong, you should have a correction ready. So when you're when you have a chance to present it, you should be able to present it. It's reasonable.
Or just like what formula you think is the correct globe formula for distance.
It's on the screen right now, almost. This is
Okay,
pretty
but
close.
I don't see the mathematical calculation there. But okay, I see a Jesse drawing. But
it's the inverse of this. To get the delta height from the baseline, from a flat baseline, the observer's horizontal, you multiply the tangent of the angle times the distance, and you get the height that's above the horizontal baseline. So that's the 511 meters in this particular case. This is Blinn Mountain from Edith's. So what you're doing though, and so you can see if you take the tangent of 43 arc minutes times 4,900 meters, that gives a delta height of 511. But that's on a globe, that's not the actual height of the mountain. That's just the part that's above the Earth curve drop, if Earth is a curved, right? The total height is, say, 642. So to reverse this process, you would take, since you do tangent of the 43 arc minutes times 4090, and that gives you 511, you would take and divide the 511 by the tangent of 43, and that would give you the 4090. So what you're doing though is you're not taking the tangent, or you're not dividing the 511 by the tangent of 43 arc minutes. You're dividing the full 64 or 642 by the tangent of 43, and that is not, even if Earth was a globe, that still wouldn't work because that is not geometrically correct for a globe. Does that make sense, or what?
So you're subtracting Earth curve out, and then you're putting it back in when you're trying to measure things with your angle. So you got your angle, which is lower, and then, I got to measure something with it. Hold on, let me add in the Earth drop back in so I can get back to what I started with. Boom, my height matches. Terrific.
yeah, that's what they
dude.
do with celestial navigation as well. It's what they do with the dip angle. They add the radius and subtract it. But yeah, go ahead.
Yeah, Jesse.
Let me ask.
Jesse, if you want to use the apparent stuff, you have to use the relative apparent elevation, right? You're trying to interject back in the true elevation, which was already taken out, and accounted for in the angle process for the different predictions. And now you're trying to put it back in and be like, look, it matched. Like, dude, that is like, and you're talking about people being honest and looking for the truth and being genuine, bro. You straight up just walked yourself out of the conversation with this dog shit diagram that you presented for the 30th week in a row, doing the same optical argument that Ruhif just did. What you just did is equivalent to the circular math that Ruhif just presented, dude. I thanks for coming by, dude. Does anyone else have any? Oh, let's finish this fucking PDF real quick. Hold on. All right.
Yeah, we do have a question.
Is it a single method instead of an array of methods and adjustments which correct for the outcome? Same method as always. The only thing that we've adjusted is the analytical process where we've added error bars now. That's it. Nothing has changed. The only thing that's changed is I've added more ways to calculate the globe because everyone is upset with how we're calculating it. How you want me to calculate it is you want me to post-dict it, put the globe back in after we already accounted for what the globe would have as drop for the physical intersection angle. Congratulations, Jesse. Has nothing to do with what we're doing, bro. And if you go around telling people that that's what we're doing, then that's sickening.
Where was that contention? Where was that contention months ago?
Just
when you guys first set out to do the measurements, why did it change?
Because we started deriving distances and elevations because the initial claim that the optical angle is like the important part, that what it would be, what the optical angle corresponds to. They were like, look, some of them are globe, but then when you analyze them, none of them give globe unless you add an error bar. Then it becomes an indistinguishable from certain predictions from flat Earth and globe, but across the other measurements where the true position and refracted position aren't intersected, then it's conclusively one-sided. And then you look at their refraction analytics, they're tripling their refraction over drop, dude. Like, look at the Mount Blinn one, right? Your boy old Blinny over here. They predict what do they predict in drop? They predict 38 meters in drop, and they have 133 in lift, dude. Like, just get out of town. That's not even the whole globe is built off of apparent optics where they've corrected things to go like, oh, it just happens to look like it's flat because of refraction. So an interesting relationship here, right, that Mike pointed out was when you do 360 times the distance to get the full drop to what the star would be predicted at, their refraction correction is always half of that. And then that gives them, or it's always like just about half. It might be off by like 1 arc minute, but it'll always give them what they expect back in angular drop for drop over distance. So like they predict 27 arc minutes for the position of the star with respect to the observer to subtract from the flat Earth angle, and that gives them 204, which is where they predict the true position is for the observer at the time. And if they add 12 arc minutes back to that, they come back to 217, which puts them at the raw geometric globe. So it's like their whole thing is basically just making up what should be there and drop, and just saying it's a refraction correction 1-to-1. So
they're trying to revert it back to the geometric instead of using the optical. Am I understanding that correctly or no?
So when they're so they want to use the optical all the time, and they're like, but it got occluded at 218. My 218. So when we start deriving things based off of that, it doesn't match up. So when we do that, the reason it doesn't match up is because the elevation of the mountain isn't physically lower than what was measured. So what they're trying to do post measurement is go, oh, you know what? We actually need to add that back in and do the full elevation. What?
Yep.
That's insane, bro. Your elevation difference can't,
right?
Your elevation can't be my elevation. We don't both live on a flat Earth. I mean, you think we live on a globe, so you don't get to have the same thing. Like, dude, that's so absurd, man. And then
light bends. Just a quick question.
To hide it and try to present it as if it's something else retarded.
Do you think light bends?
Yeah, we've got demonstrations of it that we went over earlier.
Nobody's disagreeing with that.
Okay, just making sure. Not sure, because I mean,
Nope.
There's other things that I feel like all the flat earthers were on the same page before with stuff like sunsets and whatever, and then things seem to be contradicting themselves. But there was some guy that's asked 3 times if he could ask a question.
Oh, sorry. Who was it?
Who was that? There you go.
Hold on, we got a 42-page PDF together.
Oh no, we're good. That was the last question. He just asked about the other thing. What are we at?
Yeah, can I ask a question?
Oh, Gary? No, absolutely not.
Poor Gary, just let him ask.
Nah.
Nobody cares. So.
Yeah, sorry, Gary. We're not taking Gary questions tonight. I think Electric had a question he wanted to ask.
That's tough.
I'll do one electric question, and then we're gonna wrap.
Sorry, Gary. Again, we're not taking Gary questions tonight. Electric had a question that he wanted to ask.
Hey, what's up? Yo.
How's it going?
That being said, Gary, I appreciate you being on good behavior since I unmuted you. All right, so my question is, why doesn't the elevation angle to Pikes Peak match your flat Earth trigonometry prediction?
The peak is 39 meters higher, I guess. That doesn't even make any sense, bro. We predicted an angle of 231, or no, I'm sorry, 230 for Pikes Peak, and it got occluded at 232. It's like it's 2 arc seconds higher than what we predicted. Certainly didn't match what the globe predicted.
Yeah, the time that it appeared occluded did not reflect 232, and that wouldn't be the flat Earth prediction either way. You're pretending there's no atmosphere.
Oh my god, dude! All right, just hold on a second. Let me just. I can't do that again. We're not pretending that at all. We're referencing the physical intersection angle at the peak. So that's it. If you've
Your reputation counting.
deviated from that, like I don't have the patience to listen to you go through that.
Maybe Gary's question would have been better.
Dude, actually, you know what? Hey, Gary, I'm tagging you in, coach. What's up, bro? How you been? What's your question, Gary Bear? You're actually right.
He's asking Gary. You were asking him about Earth Drop. It's all about Earth Drop. Go ahead.
Oh, he left. Respect.
What? The one time we want to hear from
Dude,
Gary.
the one time I was gonna tag Gary back in. Oh, that's hilarious. All right.
Poor Gary. I got one more question. So
That's
What you got?
hilarious.
So if an actual object has to be occluding light, then how do sunsets on a flat Earth?
Ooh, great
'Cause
question.
the horizon isn't blocking. Like you've seen that scuba video by now, right? I know somebody brought this up to you like weeks ago, right?
So-
Jake, I think, brought it up.
So I haven't seen the Skiba video. There's the one video that I'm aware of where he has the sun on a mirror thing and he's moving it
Paper,
away and it
yeah.
looks the same or whatever. But yeah, so the answer to that is just limit of vision. So at a certain point, it just gets too far for you to see. Same with the stars. Otherwise, how do the stars set?
So because there's times that I've heard you guys say that the horizon is apparent. So in that case, would an apparent object be blocking a light source?
No.
No, because it's moving away and there's atmosphere between you, so it's limit of vision and through the atmospheric what do you call that? The obstruction.
Opacity.
It's the atmosphere. there,
Okay, so
not
the
actual-
atmosphere can be counted when it comes to sunsets, just not occlusions of stars.
When you don't see them because it's far enough away and there's nothing blocking you, that's a different scenario. In this scenario,
Yeah,
there's something
exactly.
between you and the star, so it's not exactly analogous. Because if there's nothing between
Not
you
at
and the
all.
star, they just set in due to the limit of your vision, same as the sun.
Also, if you live in a valley, you'll have different sunrise times, and they'll be based off that what you're talking about. So, like,
So the
you know.
horizon.
Yeah, like just
Oh,
before it's blocked.
are they
just before it's
based off of the
occluded, you
physical
can see it.
occlusions too, Torah, for the valleys?
Yeah, like if you're in a
Oh, that's
valley or
so,
something. Yeah, yeah.
that's so interesting. I was actually looking at when I came across the archaeoastronomy stuff. There was this mountain peak range that the sun occludes or emerges from. Sorry, and it goes through these different sections throughout the year. So like each peak, like each equinox and solstice and all that stuff is marked by which peak it rises at. And it would be really interesting to do like something with that, but the sun's like half a degree, so it'd be hard to kind of figure out when would be the ideal position to calibrate that reference from. But anyway, that's interesting that the
very
occlusion
cool.
times are based off of that. That's hilarious. That proves that, or that goes with our point. I have to look into that. That's a great way to supplement it. Well, all right. If that is it, we will wrap up for the night, and we will come back next week.
How come you guys are allergic to 3D graphs? I've seen only like 2 or 3, but you have several.
I'll give you a taste of the 3D galley. I got you. I got you. Oh, it can't be a combo graph, dude. Can't be a combo. So we got to duplicate. And we got to switch to a
I need that
straight bar.
3D graph.
Got you, galley.
Hey, I have a quick comment.
Woo!
Oh, look at
That's
that.
a 3D graph right there. Ooh, all right.
Look at that.
Okay. Okay. All right.
LNG. I have
Immediately
I have a
control
quick
Z. That's what I did
comment.
too.
What's up, what's up, Lily G?
Oh, I was just gonna say that I think it's. I agree with Gally. I think it's important to have people steel man our position. Otherwise, they end up wasting so much time asking such basic questions, like why does the sun go out of view if there's no actual mountain peak, preventing us from seeing it? Stuff like that. That it just turns into a waste of time because we're just repeating really, really basic concepts.
Well, the basic stuff isn't so much an issue, right? Those are fine because it's like, does it make sense with other things and stuff like that? But it's the coming into the conversation with like, hey, what would happen if I used a different elevation angle and put back in what was already subtracted out and then derived the distance? Like that's just like sneaky underhanded dog shit. That's like insane. But like people having questions about stuff isn't an issue or whatever. Like those are well welcome. Sneaky fucking
Unless they're trap questions, those little gotchas. Aha!
Yeah.
Get out of here with that.
Dude, what is this, dude? Does this make sense given what we're already presupposing and assuming and correcting and and adding back what we already took out to do the prediction first in the first place? Yeah, dude. Hats off to you, my boy.
I don't think hold up a second. I don't think